This is lecture 17 on chapter 15. So today we'll be looking at instant center and acceleration. We'll also do a little bit of review on velocity. As you recall from lecture 16, we talked about plane motion velocity, and we did several examples of it, showing how the velocity of a point can be related to the velocity of another point, and then the velocity of that point relative to that point. And so, for example, if we know the velocity of B and we know the velocity of A, we can relate the two with the relative velocity. And then using omega cross R, we can determine what that relative velocity is. Anyway, that's easy to say, a mouthful to say, but really the application is where through repetition is where you're going to understand this concept. So if you haven't watched lecture 16, then this will be a little more difficult to follow. So be sure you watch that first. So before we jump into the idea of instant center and acceleration, I would like to do another example of velocity. Now, as we go through acceleration, velocity will be part of the acceleration problem, so you'll get more practice on those. But I chose this problem in particular because it looks a lot like a homework problem. Only difference is you have different knowns. But I wanted to show you how this can be solved in either using vectors or it can be solved with triangles. Now, I think the vector method is probably going to be more common, but I will show you the triangle also. So here we have rod AB. It can slide freely. So at this in this example, we're told that at the instant shown, the angular velocity of the rod is 4.2 radians per second counterclockwise. So since it's counterclockwise, we can determine that A is moving to the right and B is going to be moving up the incline. So what we want to know is, because of that angular velocity, what are the velocities at A and what are the velocities at B? So we're going to use the same methods that we used in the previous lecture to solve. So let's first draw what we have. So here on my paper, I have the velocity A, I have my bar. I know that the bar is 500 millimeters long, or half a meter. And I also know that this is 300. This is 125. So that makes this triangle a 3, 4, 5. You can see that. And if you look close at this, the 300, 125, that makes this triangle a 5, 12, 13 triangle. So that's a 5, 12, 13. And this is a 3, 4, 5. Okay. So that'll come in helpful when we're going through the process. So we want to know, we know that VA is there. Of course, VB is going to follow this. And then you remember that because in plane motion, we want to fix one of the points. So we're going to draw our relative velocity, VB relative to A. And of course, that's going to be perpendicular to the bar. So now we have VB relative to A. So we have this, we have this, we have this. Now, remember that we can calculate the VB relative to A because we know that from a scalar point of view, it's just going to be times R omega, right? So we don't, and that's just the scalar in that, and we haven't determined its direction, but we know that its magnitude then is just going to be 0.5 times 4.2, and so we get a 2.1 meter per second. So we know now that this is going up at 2.1 meters per second in that direction. So you can probably see where this is going is if you want to do a triangle, because if you know the angles and you know one side, then using law of sines or cosines, you can determine everything else. Or you can just find the directions of these vectors and calculate it that way, because we know that the velocity of A and velocity of B only have vertical components, but VA doesn't. So if we know that and we don't know that, we can determine it just by looking at the vertical components. So first off, we'll go ahead and we'll write, let's see what it looks like again. Draw it. And so I know that when I draw this, I know that this is going to be relative to the flat ground. So like that, the flat ground, I know this is going to be a 3, 4, 5 triangle. All right. Because we know that because this has to follow the same. So when it's down, it basically does this. So we know that the angle with the vertical is the same as this angle here. So this horizontal angle, or we can just use 3, 4, 5. If you prefer, you can use the 3, 4, 5 to find the angle here, which you'll know is also this angle in here. So if I draw it a little bigger, there's that, there's that, there's my vertical. So I know that that's going to be for this triangle, going to be a 3, 4, 5. And for this triangle, it's going to be a 5, 12, 13. I'm sorry, this arrow or this vector. Sorry about that. And so here's my VB, here's my VB, here's my VB relative to A. So now just from looking at it, so if you like trig, this will be easier. But if you don't like trig, then you want to bone up a little bit because it does help. So if I write my VB equal to VA plus VB relative to A, then first off, I'm going to break up my VB relative to A into its I and J components. So VB relative to A is going to equal negative 3/5 of 2.1 I plus 4/5 of 2.1 J. So that gives me a negative 1.26 I plus 1.68 J. There's my VB relative to A. And then if I look at my V velocity B, then I'm going to go ahead and look at just the I components, right? So I know because velocity A has no I components, so no J components, there's no vertical, then I know that whatever this 4/5 of VBA is, then that's going to relate to what this is. So effectively, what I can do is I can say VB times 12/13 equals, and this is in the J direction, and that's going to be 0 because VA has no J direction, and then minus 3/5 times my 2.1, which was just this over here. Okay, so that should answer that should give us what that value is. Sorry about that. I just realized I was writing the I component, not the J component. So again, we have in the J direction, we have VB. Here's my VA in the J, which is 0. And here's my VB relative to A, J component. So if I solve, I get VB equal to 1.820 meters per second. All right. So, and that's just the magnitude of it going up the incline. And that's what we want. So now I can do the same thing. I want to find out what I is. And so if I go with I, then I know that that's going to be, again, my 5/13 of VB, of VB. So 5/13 of VB, which is I now know to be 1.82. And then that's going to equal VA, and then minus my 1.26. So if I solve, I end up getting a value of essentially 0.7 plus 1.26. So it ends up being about, what is the value? Yeah, about 1.960. Yeah. So if I solve for this, I move that to the other side, I get a VA equal to 1.960 meters per second. All right. So all I did, again, was have this. I have that. Knowing that made it kind of easier because then I could right away find out what this was. And how do we know? How could I equate these? Because I know that this relationship, and you'll probably have noticed that we do this a lot where we know that this exists. So therefore, if we separate into the X and Y or I and J components, then we know that these two respectively have to be equal for their individual Y components. And then we can use that to find our VA. And that's what we did here. So this should hopefully help you with the homework problem. You're still in the homework problem, you're going to do similar. It's just that in that one, you're given what VA is and not what this is. And in the difference also in the homework problem is it's moving to the left, not to the right. So it's going to be slightly different. You're going to have, as you can imagine, your vector is going to point down instead, perpendicular, VB relative to A. And of course, your VB is going to point that way too. But the angles are still the same. So that makes it a little easier. Now, I said I'd also show it if I needed to use triangles. Okay, so this is the problem now if we were to just use triangles. As you can see, it's a little simpler. So following this original, we can see that VBA and VB relative to A and VB are here. So this angle here, VB, that's just the inverse tangent of 12/5. We get 67.38. So we know that's angle over here, 67.38. And then we know that beta is that, so it's the tangent of 3/4 or the inverse sine of 3/5. But so you get 36.86. So 90 minus that gets about 53.1. And then we know 180 minus this plus this gives us this. So that's 59.49. And so I don't need to show you the rest because you know the law of sines, but essentially, if you, like I said, if you know one side and the three angles, or if you know two angles, you know three angles. And if you know one side, then you're in good shape. So you can use the law of sines since you know this is 2.1 and you can calculate VB and VA. There might be a slight rounding error in your answer due to the differences between the two methods, but essentially it's the same. So that's another way you can do these problems when you have just three vectors, just like in statics. Force triangles, same thing here. So it's just a matter of what your comfort level is if you like this, but you can see that this is probably a quicker way. I prefer the other way, at least teaching, because this shows you fundamentally how to go from here to here to here. And because in some cases you may have more than three forces and it may be complicated to look at the geometry. Whereas this, if you're just adding vectors, that's always going to work for you. All right. So that's the last example for now for just pure velocity. But let's look at instant center and talk about what that means. So instant center. Instant center is the idea that if you draw a perpendicular line from your velocity, that you can find a point in space which has no motion. So it's as if instead of having motion and rotation, you have just rotation. And so it's easy with one velocity because you can just draw a perpendicular line out to it. Now, when you have multiple, though, it usually is easier to um, draw multiple perpendicular lines. So what I mean by that is, let's look at the next slide and then we'll come back to this one. So here you can see that because an object has both velocity and, I'm sorry, both rotation and translation, then you have two different vectors pointing different directions, which is what you'd expect. So when you find two particular points and you go ahead and draw their perpendicular where they center, that's your instantaneous center, meaning that again, that does not move, but it rotates about it. Or if you had an example where, you know, in this case, the two vectors may be pointing the same direction, but because one is bigger than the other in magnitude, that means that this thing's also going to be translating and rotating, because the larger velocity vector means it's going to want to rotate counterclockwise. So again, we can find the instant center. And this probably easiest is when you have sliding objects that are perpendicular. You can see that if you draw this here and draw that there, voila, you basically have a instant center for you there. So these types of problems, or I should say instant center is a good tool to use to understand other problems, but it's not something we're going to do a lot of in terms of there's applications where it works well and applications where it doesn't work. It's basically it. So I will let's go ahead though, and before we look at the juggling pin from here, because we can look at that from instant center point, I want to look back to this problem here. Now, recall that we did this one in the last lecture, so you know the objective was to find the velocity of the door D. So I just want to go over this one, showing how we could have used instant center instead and got the same answer, and it would have been a slightly quicker process. So as you look at this problem, I would pause now and draw the sketch. So now, as I said, with the instant center is, as the name implies, it's instant. So it only applies for the snapshot in time that you're analyzing the problem. Generally, it's constantly moving, which makes sense. So looking at this, you can maybe get an idea of where the instant center is going to be. For one is we have A going to the left, we have B going up. So if you draw two perpendicular lines, it should be right where my mouse is. So go ahead and draw that, figure out what the angle, or you know the angle, figure out what these lengths are, and then go ahead and start the video and try to work through as much as you can. Okay, so you've probably already completed it, but let's just check the work. So here we have velocity A is going that way, velocity B is going this way, right? And we're given that this is 1.5 feet per second. So we want to find omega and velocity D. So if we draw a perpendicular, as I said, you can see it, this and this. So that's our instant center for those two. Now, remember that the velocity of D in our last problem, because the garage door is closing, it was going down like this. So it makes sense that it's probably going to be going somewhere up like this. Well, how do we figure that out? What we can do is we can draw a line to point D, and then we draw a perpendicular to it. And so now we know that's the direction of velocity D. And of course, we need to know what that angle beta is. But actually, that's not going to be so bad because we know that beta is the same as beta there, right? Because that's it. if this is 90 degrees and that angle is the same. And because we know 40 degrees, we know this side of the triangle, we know that side of the triangle. So if we know this side and this side, we know that angle. So again, trig is your friend, but so I know that, and we call this C, point C for instant center. And we know that this distance is going to be 5 cosine 40, 3.83, which equals 3.83. So we have 3.83 feet there and 3.83 down here, since it's the same distance, same hypotenuse. This distance here, we know that's just going to be 10 sine 40. So that gives us 6.428. Well, now that we know this side, we can use tangent. And so we know that beta equals the inverse tangent of 6.428 over 3.83, which gives us an angle of 59.2 degrees. So 59.2 degrees. All right. So now, because we know the distance of the amount of the velocity versus the omega, backing up, we have this. We have CB. So that distance to there, we can find that using sine also, and that's 3.214. And so what we can garner from that is we know that the velocity of B is equal to r omega, or omega is equal to 1.5 feet per second. And then what is its r? It's 3.214. So here we go. So now we know that that is going to be moving then up here like that. And so we get a value of 0.467 radians per second in the counterclockwise direction. And that's how we got that. Okay. And then the last part is just figuring out what is the velocity of D. Well, we know that the velocity of D can be related to the distance from the instant center, so here to here. And so what is that distance? Well, if we square this and square this, we know how to get the hypotenuse. That's going to be 7.482, right? We square root. And so now we know that the velocity of D is, again, r omega. So it equals what? 7.482. And then that's going to be multiplied by our 0.467 radians per second. And this is feet. So our final answer gives us about 3.49 feet per second, and that's at an angle of 59.2. Or you could break it up. If you were doing more work with it, you might want to break it up into components, which would be 1.787i plus 2.76j. All right. So that's how you do an instant center with this. So you have this point here, so that allowed us to pretty much use just basic trig to find these distances. And then once we knew omega from this little distance here, that velocity, we know omega has to be the same on the whole rod, so we could essentially find it anywhere. So if we extended this down farther, all we would need to do is connect a line. And so you can even see that if this was down here, then we could just do this. And we could find that by extending this down, right? And so forth. So it's a good tool to have for some problems. So hopefully that makes sense. All right, so let's go back, and I want to look at the